So hopefully you're here because you believed me when I said that mechanisms make more sense when you see examples and you apply the idea. So we've got a three-step mechanism here. We have Cl2 breaks apart into C2Cls. That'd be a unimolecular collision. We have Cl reacts with CH3Cl3 to make HCl and CCl3. We have Cl plus CCl3 makes CCl4. In this one, it tells us what's fast and slow, and over here it doesn't. So we'll see how those two things are different. So some important pieces here is where we need to support an overall reaction. We need to support a predicted rate law. So as we do this, when we're looking at an overall reaction, we would cross off anything that appears on both sides. So that two CLs would cancel out the Cl and the Cl right there. The CCl3 and the CCl3 would cancel one another out to give us the idea that we only have Cl2 and CHCl3 as reactants, and we have HCl and CCl4 as products. And if we're doing this on paper, crossing those off would be a great way to show that throughout that process. When it asks for intermediates or catalysts, we have no catalysts because that would be something that is consumed in an early step but then produced again later. We do have intermediates. Cl is made, but then we use it up. CCl3 is made, but then used up. Made, then later consumed. In this one, the first step is fast. So that'd be like mixing up our batter. But then baking that cake is going to take a little while. So if we wanted to make another cake, yeah, we could mix more of this up, but we'd have to wait until the oven was empty. That's why that slows down the overall process. Or from a collision theory sense, breaking this bond goes fairly quickly, but the bonds that are being exchanged here, getting the H off and the Cl in, the H off, sorry, but not the Cl in, is a more energy requiring process potentially, or maybe it's more about orientation, so that is slow. When we are trying to find a rate law, we would kind of draw a horizontal line under our slow step. Everything up to and including that slow step is determining how fast the overall reaction can go. So the collisions here and the collisions here determine how fast the overall reaction goes, but it doesn't matter how fast you can ice your cake or how fast these last collisions can go. The overall process can't go any faster than this slow process right there. So in terms of connecting that to a predicted rate law, we can't just look at our coefficients and know for sure, but when we apply it to a mechanism that we assume to be correct, we can say, well, Cl2 only collides one time before it slows down, and CHCl3 collides one time before it slows down. So if I put more of this in, that would make the process go faster. If I put more of this in, that would make the process go faster, because each of those would have more chemical available to have their step speed up. So each of those appears one time, and therefore the rate law would be predicted as first order relative to Cl2 and first order relative to this. This last one, if it had any reactants or if it had another instance of something from up there, would not be included in our rate law. This mechanism is only 2 steps. And as we look at it, it's fairly simple. The one that I showed in the notes with 10 steps was just to show how they could look. Often we'll see 2 to 3 steps. Maybe 4 steps is going to be the longest that we would see. So we would combine these, and we would see that there's 2 NO2Cls. The Cl cancels with the Cl, so there's 2 NO2s, and there's 1 Cl2. That's our overall reaction. If that's the reaction we're being asked about, then maybe this mechanism would work. We have no catalysts, once again, nothing coming in that is made later. And once again, Cl ends up being a intermediate. Kind of random that it was the same in both of these. So here we are going the other way. Maybe in a previous step, we are doing a differential or integrated rate law. Maybe we've got a nice curve that is flattened out by 1 over the concentration of NO2Cl. So we know that it's second order. So if it is second order, we have to think about, what does that mean for this reaction? That means for this reaction that the NOCl2, increasing the rate of that increases this step, but I need it to appear 2 times, as if adding 2 of those molecules makes it go even faster. So that's why in this instance, the second step must be the slow step. NO2Cl must appear 2 times in the mechanism up to and including our slow or rate determining step. So the rate law indicates it that that collision, or the collision of NO2Cl, factors in twice. So we have to have 2 reactions that use that. So the second step is important to our overall rate. If we had different data that said it was first order, then that might mean that this first step is slow. We could draw a line there, and no matter how much I put in, it doesn't go any faster than this, because maybe in this instance, breaking off that Cl just requires a lot of energy or the perfect orientation. So mechanisms, and oops, right there, are kind of the last piece of putting our experimental data together with our collision theory, together with our orders and our rate laws, to get to understanding what's actually happening. And more repetition through practice problems and AP questions over mechanisms is very helpful.